Hello everybody, welcome to the next video in this series of Physics at Home, Electromagnetism. Today we're going to talk about two circuits. One circuit is resistors in series and the second circuit is resistors in parallel. Look at the arrangements of the two resistors that are attached. Okay. Now we're going to explore a little bit of theory of these two first, and with our understanding of Kirchhoff's laws, we are in a much better position to explore these two circuits. What we can see here is resistor 1 and resistor 2, they are connected back to back. Now this situation here is similar to the Kirchhoff's voltage law circuit that we saw two videos ago. Okay, what we realized during that is the current that was flowing in this circuit here through the resistor 1 and resistor 2, both of those had the same exact current flowing through them, correct? That is the characteristic number 1 for resistors in series, that both resistors have the same current. Whatever amount of electrons that enter here, so the R1, they leave and then they enter R2, right? So the current on the left and right, both of the resistors is the same. The second characteristic is voltages across R1, which is voltage 1, and R2, which is voltage 2, add up to the voltage applied. So in our case, voltage applied is this voltage here. This is going to be equals to the voltage across 1 plus the voltage across 2. So the voltage applied gets distributed, voltage 1 and voltage 2. Now it depends how much is voltage 1, how much voltage 2, depends on the resistors 1 and 2. The higher the resistance or lower the resistance, that will if they are equal, that will make a difference. Okay. Now with this information in hand, let's take this a step further, that the voltage applied is equals to voltage 1 plus voltage 2, correct? Now using the Ohm's law, we know that voltage is current times R. Voltage equals to current times R, right? So that's what we're going to do. Now plug this IR into each one of these voltages here. So on the left here is going to be I multiplied by R. And then voltage 1 is the current through 1 times the resistance of 1 plus current through 2 and resistance of 2. Now we already know that the current 1 here and then current 2 here, they are equal, correct? We call it current I. So all of these currents, I1 and I2, they are all the same. So we could say that we can divide both sides by current I, and these currents cancel out. Yeah. Then what are we left behind is the resistance of the 1 and 2 together. The total resistance of this circuit, which is for this is a series circuit, is nothing but the resistance 1 plus resistance 2. So the resistances add up when they are in series. Okay. Now let's look at resistors in parallel. They also have two characteristics. Okay. So let's look at the current first here. So current is flowing in this direction, and we probably can notice now that there is a junction here, right? At the junction, the current is going to get split. So a part of it goes through current resistor 1. We're going to call this I1, and the other is going to go through I2, resistor 2. And at the junction, if we remember from the junction rule, that current enters is the current leaves, correct? I equals to I1 plus I2. Now let's take this and make the note here. Currents across R1 and R2 add up to the total current in the circuit. So meaning when these currents 1 and 2, they come and meet again at this junction, then they add up and go out as current I. Okay, so I enters, gets split, and then whatever gets split, they get add up again, and then I leaves. Okay. The second characteristic here, voltages across R1 and R2 are the same. So now think about it here. This is a bit tricky here, but if we realize that if I place my voltmeter here and try to measure voltage 1, then the two probes of the voltmeter, if I place them here or along this line or at the junction, again, here or along this line or this junction here, it doesn't matter. Within the line, there is no voltage drop. So it is as good as saying that I can place my voltage probes at the junctions, correct? Then the same junctions also can be applied to the voltage 2, correct? So if I'm putting, voltage 2 here, I can place it, wherever I want, correct? So I'm measuring the voltage across the same 2 points. And if you look at the applied voltage, is also within the line, there is no voltage drop, correct, in both sides. So for all three of them, across the junctions, these two junctions, the voltages is going to be the same. So voltages across R1, R2 are the same as applied voltage. And we will do a demonstration of this. And I will show you that indeed the voltage across 1 and voltage across 2 is the same as the voltage that was applied. Okay. Now let's take the first characteristic, the I equals to I1 plus I2, and apply Ohm's law to it. So if we remember, current is voltage over resistance, correct? And that's what I'm going to do. I'm going to take this and plug it as I1, I2. So this becomes voltage divided by R, right, equals to voltage 1 over R1 plus voltage 2 over R2. And looking at the second characteristic, we know that voltage applied equals to voltage 1 equals to voltage 2, right? Yeah. So meaning all of these voltages are the same, so they would cancel out. And what we left behind then? 1 divided by resistance here. Now this resistance is the total resistance of the two resistors connected in parallel. So this is R parallel equals to 1 over R1 plus 1 over R2. Yeah. So these two equations give us an idea that, hey, if we have resistors in series and resistors in parallel, then we can expect to measure the total resistance of the system. Okay. And this is what we're going to verify, that the theory tells us that this is, R series and R parallel. And I'm going to demonstrate here in the next section of the video that we can create this circuit 1, which is resistors in series. And what we're going to do is we're going to change this applied voltage. Applied voltage is going to be approximately 3, 6, 9 and 15 volts. So we're going to change the voltage and we're going to change the current flowing through this circuit here, and we're going to plot it. Okay. So voltage here and current here. Then we would see that if you increase the voltage, then the current should increase as well, correct? Because voltage equals to I times R, right? The resistance does not change, right? If V increases, I should increase. Then we're gonna expect a plot something like this. Yeah. And then this plot here we're gonna do using Excel, and using Excel then we're gonna get equation of this line here. That line equation is going to come out in the form of y equals to mx plus b. So b is the y-intercept, and it's going to be almost going to go through the origin. So our b value is going to be approximately 0. Yeah. So then y equals to mx. Okay. So if we compare this line equation with the Ohm's law equation, yeah. So then maybe I could replace, switch the two terms here just a second. Mx or xm doesn't matter. If we look at this here, voltage is on the y-axis, correct? Then x-axis is the current. Yeah. Then the slope of this line has to be the resistance R. Okay. So slope is going to be the resistance of the circuit. Yeah. Now since we're going to have resistance 1 and 2 together, and we're talking about the whole circuit, so the slope here is going to be R series. So R1, R2 we would know to begin with, and theoretically, we can predict that how much should be the slope of that line. And we're going to see how close does it get to the theoretical value with our experimental data. Okay, so let's look at the demonstration of this circuit on the left. Okay, so here are the two resistors, and I already measured their resistances. This one is about 1788 and this one is about 1186 ohms. So these are in about thousands. So let's just, yeah, about 17, yeah, there you go. So around that, 1788, 89. And this one, yeah, 86, right? So these are the two resistors, and we're gonna create a series circuit, right? So this is how they're gonna be back to back connected. All right, and then the two ends of these are to the applied voltage. And if we remember, the applied voltage is supposed to be anywhere from it's going to be 3, 6, 9 and 15 volts, correct? And looking at these two batteries, you probably guessed how we're going to connect them. But if you haven't, let's see how. So I have a 9 volt and a 6 volt, and I need 3 volt coming out of it. If you remember, this is kind of similar to the end of the video about Kirchhoff's voltage law, when we mentioned that what happens if you flip the other battery, right? So what will be the total voltage between the two? So I can hook it up here and we can see what is going on. So alright, so from the negative of the 9 volt, I'm gonna connect to the negative of the 6 volt. From the negative of the 9 volt to the negative of the 6 volt. So the way this is gonna look like is this. Alright, so the 9 volt is here and the 6 volt is here, correct? And we want to know how much will be the total voltage if we try to measure it between these two, like that, correct? So if I do it like that, and then remember, 9 is at a higher potential than the 6, correct? So if I connect this, oops, it's about 3. So whatever is the difference between the two now becomes that voltage, correct? So if you see it here, this one is, oops, 9.53 and this one is 6.36, right? So the difference between the two is this voltage, right? So voltage 1 is 3.18. I'm going to create a table here. So voltage 1 was 3.15 or 1618. Okay, 3.18. Yeah. Voltage 2, we said 6 volts, right? So that means we're just going to use this one battery and that's it, right? So let me disconnect that. Let's measure the voltage of this battery. And this is, so positive is here. 6.36. So the second scenario is just 6 volt in this direction. And I always tend to forget. So this is, the second, right? Now the third one is going to be just the 9 volt. So with just the 9 volt like this, let's measure the 9 volt. 9.53. And finally, we need total 15, right? So you guessed it, right? 9 volt and 6 volt are supposed to be now back to back, which is you can see now the 6 volt here and 6 volt here, I'm switching the polarities, correct? So 9 plus 6, the total has to be added up together, so which is now from the negative of the 9 we connect to the positive of the 6. Alright, so there you have it. And we measure the total voltage, from the negative of 6 to the positive of 9. 15.88. Alright, so we get 4 voltages. And for 4 voltages, when we hook them up to these resistors, we're going to get 4 different currents, correct? And we'll have 4 values of voltage and corresponding 4 values of the current. So let's create the table here. So voltage, current, right? So the first one is 3.18, then 6.36, 9.53, and 15.88. I want to know how much is the current flowing through between, for each situation. Okay. Now to measure the current, okay, I could, if we remember that our circuit is like this. And we have resistors 1 and 2. And to measure the current, we have to hook up the multimeter in series, correct? And either we do it here or here, it doesn't matter because the current is the same between the two, right? So what I'm going to do is I'm going to hook up the multimeter has an ammeter here. Okay. So let me do that. So make sure I go to the current region here, the function. Range we can select later. So we are expecting that our applied voltage, we always want the positive and negative in that fashion, right? So we want the current to flow in this direction. So current, it's gonna leave R2 and then gonna enter the negative of the applied, correct? So that's what I'm gonna do now. I'm gonna just leave it here so I don't have to mess with a multimeter again. I once saw a student doing it in this fashion and it tidied up the circuit quite a bit. Okay, so here, okay, and current is here, so I'm expecting the current to enter through the red here, or the input. So I'm gonna hook it up here for the red, and it's gonna leave from the black. Alright, so it's gonna leave from the black. And it's gonna hook up to the other side, correct? To the applied voltage. Now, one thing we're gonna be careful here is always to make sure that when we're doing 3.18, 6.36 and all of these, that always the positive or the higher terminal is always on the left side, okay? So that always our current value here will turn out to be a positive number. Okay, so we have all of this now. Okay, and now these two ends are ready. We need to connect to the batteries. Okay, so let's begin. So if we remember, in the first scenario, we connect negative of 6 to the negative of 9. Okay, so negative 9 goes to the negative of the 6. Maybe I could do it like this so we can see. Alright, so negative to this negative. Okay. And then these two ends, one here to this guy. And as soon as I connect this one over here, I'm going to see a value for the current flow through, correct? Because right now it's open and I need to close the circuit. And there we go. Oops. Okay, so this is 1, so that means it's higher than 200 micro. So, alright. So I get 2000 micro. So it's about 991 and it's the smallest of the voltage. And as the voltage increases, it's going to go higher than this. So, well, let's see, I can write this down the way it is, or let's see if I go up here. Well, yeah, I like this idea. 991. Okay, so the current here is 991. Well, okay, it's settled there, so let's put that number. And then 10 to negative 6, because this is micro. Okay, now that is for this. Okay, it's still increasing, but it's kind of stable there. So now disconnect this. Now we just want the 6 volt, correct? So let's disconnect. Alright, so we just want the 6 volt. Now remember, the positive of the 6 volt has to be on the left and negative here. Okay, so now we can connect here again. Alright, so it's gone beyond 2000. Okay, So now it's 2.11 milli. Okay, so 2.11 10 to negative 3. Okay, that's the current. Remember, again, just pay attention to these little symbols here, the prefixes, the mu and m. Mu is the 10 to negative 6 and m is the 10 to negative 3. Alright, so we got it now for the 6.36 volts. Okay, so we got it for 6.36 volt. Now we want on just the 9 volt. 6 on the side, and the positive of the 9 is supposed to be on the left. Okay, we got that too. So here to here. Alright, 3.11. Again, 10 to negative 3. Okay. 1, 2. Sure. Well, answering, it's okay. And then the final measurement, which is 9 and then 6, back to back, correct? So the way we connect is from the positive of the 6 to the negative of the 9. Yeah. And then these two sit on the negative and positives respectively. Okay. So this is connected, and as soon as I hook this up, we'll see current 5.2. Okay, so 5.21 10 to negative 3. And there you have it. This is how we run this experiment. That we have 3 voltages and we need to measure 4 voltages and 4 corresponding currents flowing through this circuit. Now, just for the sake of information here, we can verify that the voltage drop, the first characteristic that we understand, is the applied voltage is the same voltage. Is the voltage 1 plus voltage 2, right? So we can, just for the sake of our information, we can see it here. So now I'm measuring voltage. Okay. Now applied voltage, is about 15.88, correct? So voltage across 1, 9.43, so 9.43 plus, let's see, voltage across the second one, 6.25. Let's see if they add up to, I already see 9 plus 6 is 15, and then 4 and 2, so this turns out to be 15.68. Close to it, right? Pretty close. 15.88, 15.68. So the characteristic that we understand about resistors in series is, we can verify that the voltage applied is equals to the voltage, gets split between R1 and R2. Now in the next section, we're gonna see how we can take this and using Excel plot and get the equation of the line, and we're gonna see indeed if the slope of the line, how close does it get to the sum of these two, right? Because the total slope is the R1 plus R2 for our series, right? Now before we do that, let me just give you a quick teaser of how resistors in parallel can be connected. Okay, so everything is the same. Okay, so let me disconnect these here for a second. Yeah, and the way we can do resistors in parallel, so if you remember, it's gonna look like correct. So R1 and R2. Yeah. So I'll bend this here, and I'm gonna bend this one as well, and the same way. Right, so you can see now how these are, connected like that. what I'm going to do is that these two together connect like this. Right, so this together, and then just want to make sure that so make sure you put it on top of each other, because if they are kind of on the side, then they it could loosen up the connection. Okay, so make sure they are on top. All right, and also follow the same for the other side. So let me bend this here. There we go. All right, so you can see now how these two are connected, right? See, in parallel. And now these two ends, they are going to need to be connected to the batteries, correct? So let's try a 9 volt here, just for information. Okay, so we want the voltage applied to be in this fashion. Yeah, so applied voltage. So the current is in this direction. All right, so let's see. That's a positive here, negative here. All right, so I already connected now these in that fashion. What I'm going to verify now is indeed if the voltage applied is equals to the voltage drop in between each one of these. Okay, so this is Alright, so let's see how much is the voltage applied. So from here to here, hopefully it will be stable. Right, so about 9.3, something like that. Now let's see what is the voltage across this guy. See, it's the same. How about this guy? Yeah, 9.3. So voltage across these two is the same. The current is different. Whatever the current is entering is going to get split at this junction, and then I1 and I2, and then they meet again at this end here and goes out. Okay, now you could also, using wires, you can create it a little bit more flexible, in the sense that you can actually measure the current in this, and then the current that goes out, and then through 1 and 2, and then verify that too. Okay, so try this one then, and do the voltage and then current measurements, and then plot again, and then see if the slope of the line is equals to the equation that we see for 1 over R parallel, right? So in the parallel, 1 over R parallel is 1 over R1 plus 1 over R2. Okay, so let's go to the Excel now. Okay, so here I have created a table, and on the piece of paper the voltage was written first but the current later, and I have switched them. Okay, because in the Excel, the way I'm gonna input the plot is it's gonna consider the left column as the x-axis and y as the right left column as the x, and then the right column as the y. So just be careful of the current values when you put in there, right? Remember, my first value was 993 micro, right? So if I plug in 993 exponential -6, okay, so if I plug that in, then that Excel is able to read that, and what it's going to do is going to make it into a move the decimal place 2 places to the left, and gonna give me 9.93 10 to -4, which is the same as 993e -6. And the rest of them, were just, the 2.11e -3, and then so on, right? So it's very critical that you input the correct value of the current in the correct unit, which is amps. Voltages as is, okay? And we have our resistance 1 and resistance 2, right? Now the way I'm gonna input the plot is select these two columns, which is you place the bring the mouse here and then left click, okay, and then drag. Okay, so you can select both the columns. Once you have selected them, then come here on the top, and in the insert tab you're gonna see charts, right? So click on this, and I'm gonna use just the dots. Okay, so scatter. So now this chart here, let me make it bigger. Okay. So as you can see, on the x-axis is all the current values and y is all the voltage values. If I had flipped the columns, then voltage would have been on the x-axis and current on the y. That's why I put the current first. But there is also a way to switch the axis if you don't have the two columns right away. So anyway, so as you can see, we see a linear trend as it is. As the voltage increases, the current has increased too. Now what we want to do here is add a trend line. That one is in the option, the chart tools option. So for example, if you're outside here of the plot, then you don't the options that you see on the top, there is no chart tools. So those options don't get activated until you select the chart, which now you can see here. And under the design tab on the left here, you're gonna see add chart element. Click, go all the way down, you can see trend line, right? So for this trend line, we just don't want the trend line, we also want the equation. So we need to open the more trend line options here. So click that, and you can see on the right here, now it has opened a panel where it has selected a linear trend line. As you can see, it's going through nearly all of the points. What we want is equation, so which is this option here, display equation on chart. Select that, and bingo, it gives us the equation in the y equals to mx plus b format. And I'm gonna increase the font size here. Okay, so as you can see, the subscript b is almost 0, right? So we can ignore that, and all we care about is y equals to the slope times x, correct? So looking at this now, the slope 3025.2, that is my slope, correct? So 3025.2. Now that pretty much is giving us the information that the total resistance now, as we saw earlier, is the slope of this line, right? And the total resistance for series is nothing but the sum of these two, correct? So that's what I'm going to do. I'm going to write an equation here. So equals to sum, okay, sum of these two. Yeah. So close it and then say enter. So you can see sum of the two is 2974, and the slope is telling us it's supposed to be 3025, right? So pretty close, these two numbers. Well, how close? Let's calculate percent error. So percent error is, again, I'm going to type an equation, equals to, I need the difference between the two values. So open a parenthesis and then this value, right? So higher, whichever is the higher, minus whichever is the lower. So I'm selecting the cells. Yeah? Close the parentheses, then divided by whatever the theoretically it's telling me, right? So 2974. So divided by this and multiplied by 100. So if I do that, I get the percent error. So about 1.7% is the difference between my expected and my measured, or the value from the plot, correct, or from the experiment. Similarly, you can repeat the same thing for parallel. 4 voltages, 4 currents, plot it, get the get the line, get the equation, and then compare your R slope, okay, the slope for that plot. Okay, so just to give you a heads up here, so the same two resistors, correct, and R parallel, what I'm expecting is an inverse of the sum of the inverses, correct? So this is going to be equals to 1 divided by, so 1 over the first resistor, correct, plus 1 over the second resistor. If I do that, now that gives me a value. So I'm expecting about 713 ohms of resistance, right? So meaning with our parallel, now my total resistance has dropped. Earlier it was about 3000, now it is dropped to 700. So meaning my current values that I'm expecting are going to be much higher, about 3 times as high as the current values that I see here, right? So see if that you can verify, run your own experiment and see if it works. Okay, so this is how you can test R series and R parallel. I hope you enjoyed the video. Next week we're gonna look at RC circuit, where we're gonna hook up a resistor and a capacitor or 2 capacitors in series and see what happens.